Hey, good morning. Welcome back to science class. Today we're going to discuss the difference between molality and molarity. Yes, molarity, the way we measure the concentrations using the equation moles over solute, right? That's what we use a lot in class. We used it all last week to mix up those solutions. Molarity, the big capital M. We see it everywhere, right? And today we're going to talk about molarity's little brother, or molarity's little brother, molality, and molality with the little m, and molarity with the capital M. That's the way we tell them apart when they're written on the paper. So let's look at the equations and let's compare it. Let's go to our one we're familiar with first, molarity. Molarity, capital M, is moles of solute. That's the amount that's dissolved in it. Moles of solute in liters of solution. This is where we need to have the volumetric flask to make these solutions. That's why we need that. We need to know how much solution is totally made at the end. And the reason we need that is because it is something we like to use for factor label. Factor label. Right? If we're working with equations, if we're working with stoichiometry or factor label, we need to use molarity. That's what it's designed for. So we can know how much material we're using in the reaction. Opposed to that is molality. And molality is going to be moles of solute over kilograms of water. So it makes it a little bit easier to measure some out. If you can measure out a kilogram of water and put some stuff in it, right? And you know the volume's going to change with that because the water's going to shrink, or we're adding material in there, so the volume's going to change, but that doesn't matter anymore. We're worried about the mass of the solvent. It doesn't have to be water. In our case, we're going to use water every time. And its label again is little m. It works great for certain things, but it's not the factor label. It's not usually for factor label and balancing equations and that kind of thing. It's not going to be for that kind of chemistry. It's for a little bit different kind of chemistry, and we'll talk about that in a second. So we're going to come back to molality. There's the difference at kilograms of water instead of liters of solute. It's backwards on my screen. Kilograms of water versus the liters of solution. All right, let's look at what this molality is used for. What we call the colligative properties. The colligative properties are how a solution's properties change as it becomes more concentrated. Let me say it another way. As you have a pure solvent, so you have water, it freezes at 32 degrees Fahrenheit. If we add salt to that water, the temperature which it freezes will drop. This is why we add salt to the roads in the wintertime, to melt the ice. Well, what we're really doing when we're making a salt water solution or a ice salt solution, and the temperature which it freezes will be lower. The more salt added, the lower the temperature goes. Now, there's a limit because only so much salt can dissolve in water. If the temperature outside gets so cold, I can't remember what it is off the top of my head, then it's too cold that even the salt water freezes, and they know that's when school's canceled for sure. Right, it happens a few times. So freezing point depression is when the solution freezes at a lower temperature than the pure solvent. And our example, again, was salt water on the roads. Now, also when you used to make ice cream, if anybody has the old hand churner ice cream, right? Same thing. The salt in the ice makes the temperature much lower, the temperature it's freezing at, so the temperature drops well below the freezing point of what the ice cream mix would be, and it would freeze solid. So if you haven't made ice cream at home, we're going to do it in class, so if we ever get back to school, we'll do that at some point. Let's look at this equation really quick. Delta T, change in temperature. That little F down there, that means freezing, right? So the temperature of the freezing point, delta means change. The change in the temperature of the freezing point is equal to, Mr. Arnold, you're in the way again, is equal to the molality. There's that concentration, that molality. That's what we're going to learn today. Times Kf, which is a constant depending on the solvent we're using. In our case, we're going to use water. And then times I. I is the ions, because remember, ionic compounds dissociate. And so if it's a compound that has more than one ion, well, if it's a compound that has 2 or 3 or 4 ions, the effect of those particles in the water are going to change that temperature. Okay, now a lot of people ask me, they say, oh, Mr. Arnold, why does it do this? Remember, this is my water, right? These are water molecules. The O, and these are my hydrogens. It's polar. And it's lopsided like that. It looks like little Mickey Mouse ears, right? Actually, this really looks like rock and roll to me, right? Yeah. So we have the water molecule like this. When water molecules start to freeze, remember they have to line up positive to negative. Well, if you have, I'm going to use my snowball here as a solid particle. There it is, my little microphone. Now, if, say that this particle is dissolved in the water, right? It's in the way, right? The particles can't freeze because they have other little particles that are in their way. And since those particles are in the way, the temperature, which is the speed of the particles, the temperature has to drop lower and lower and lower until it can form that crystal structure that it wants to form. So it's interference. It's just interfering. The more particles in the way, the lower the temperature has to be. Another property would be the boiling point elevation. So boiling point goes up as the amount of solid gets in the way. And think of it as the same thing. Those particles are trying to boil. They're trying to escape. If there's other large particles in there that are in the way, again, blocking their path out of that liquid, it's their path into the sky, their evaporation, their boiling, it's going to slow them down. So the temperature overall is going to have to be higher before it will boil. So again, interference. If you just think of it as the particles of the solute are interfering with the solvent's normal abilities, you should be good to go. All right, the equation for this looks just the same, except it has a little b there for boiling. So the change in the boiling point is equal to the molality, that's the important part, times a constant, because every solvent's a little different, and then times I, because those number of ions in the way interfering with the normal boiling point is what changes that temperature. So, first, we have to look at molality. And so here we are, we're at the Schoology page, and this is in the folder originally. I'm going to move some things around. I know that I already changed and made a remote learning folder. So this number 6 molality page will be moved down into that folder, but mine's still in this folder, so I'm going to open it here. So open up molality, and there it is. I thought I didn't have a Cami version. And we're going to do this on Cami, and we'll look at this. Very similar to molarity in problem-wise, except the slight change in the equation. And there she is. Okay. Let's see what we can do with that. All right. So our equation is little m molality is equal to moles of solute over kilograms of solvent. So I'm just going to write it this way. Little m equals moles over kilograms. Now, if you want to copy and paste that into each of these, go right ahead. This would be the time to do it. You can pause this, or you can just watch me do this too. And let's go down to number 5 at least, and then we'll come back later and fix some more things. It looks like we're going down to number 6. Yeah, let's go to number 5. Okay, so same kind of idea what we did with molarity. Our main goal was to make the numbers fit the equation. We have to make sure the labels match. If the labels don't match, we make them match. All right, let's see what we have. What is the molality of a solution made from 2.4 moles of sodium chloride, that's salt, in 0.8 kilograms of water? The labels match. So all we're going to do is put them in the proper spots, right? So 2.4 moles, copy that 2.4 and paste it right in there. 0.08 kilograms of water, right? Copy, paste. If you don't remember how to copy and paste, remember it's Control C, Control V. If you have an Apple, it's Command C, Command V. All right, so we have this set up. All we have calculator, easy peasy here. 2.4 divided by 0.8, and I'm getting 3. And so our label is 3 with a little m, and that means, again, moles per kilograms. All right. Number 2. What is the molality of a solution made from 63 grams of HNO3 in 0.5 kilograms of water? All right. I always say do what we can first. Get it out of the way. We have the kilograms right here of water. Let's put that in first because we know where it goes. Okay, easy peasy. What we don't have is moles, right? So we're going to have to do a little bit of math here. So we're going to make this right here, the 63 grams of HNO3. Let's copy that. Let's paste that right here. And then let's put that into a factor label table for ourselves. So if we make a quick table here, right there we go. And we put moles on top. Remember, it's always going to be 1 mole. And then we find the mass of that HNO3. So right behind us, we can see that H is 1. Calculator, where are you? So H is 1 plus nitrogen is 14 plus oxygen is 16 times 3, because there's 3 of them, right? Push equals, we get 63. So we have 60. Save to shrink. We don't want to do that. Cancel. So this should be 63 grams. Okay. Oh. It's 63 and 63. It's 1 mole. Come on. Come on, science. Quit doing those kind of things to us. So this was just a 1 anyway. And so we have 1. One mole divided by 0.5. Why am I even pumping this in, right? Equals 2 molality. Oops, let's do it the other way. 2m, right? And so that's how that works out. So it's not too bad, right? The main thing is you get an equation and you make things fit the equation. All right, now we're going to stop at number 5 today, and that's all we're going to do, and we'll go back to this tomorrow. The answers, of course, are on the bottom, so check it out. Good luck with those last three. All right, have a good day.